Good morning, my 3 people. My 4 people now. Can y'all hear me?
Yes.
Yeah.
Yes.
That's 3. There's one more, I think. That sounded like Carly, and I'm not sure which other 2. Who else said hi to me?
Kelsey.
Kelsey and
Ashley.
Ashley. Summer? Oh, maybe Summer's not in there yet. Summer, can you hear me? Summer?
Hey.
Hey. All right, so maybe somebody else will join us in just a minute, or maybe they've already done the homework and it made 100% sense. Let's start with, did all of you check your coordinates on your unit circle yesterday with the picture I sent you via Remind?
Yes.
Yes.
Are you totally okay, and tell me if you're not, are you totally okay with how you labeled each of those ordered pairs? Do you understand where those coordinates came from at multiples of 30 and 45 degrees? Is anybody thinking, I don't really get it, I pretty much copied it down? I'm going to take that to mean, no, I understand it, right? Last call for questions on these ordered pairs on the unit circle. All right. This is the, trying to make this rotate. It's not rotating on my phone. That's the picture I'm referring to. You have your multiples of 30 and 45 degrees. What you're going to get really good at, and I promise this, if you practice in the next few days, it'll be so easy for you to look at your unit circle without all of these labels and just count by 30s. Here's what you need to practice doing. 30, 60, 90, 120, skip over the 45s, 120, 150, 180, 210, 240, 270, 300, 330, 360. So you need to be able to do that quickly, and you need to be able to count by 45s quickly. Let me just go ahead and write down what I was saying. This is 30, 60, 90. 30 more is 120. Skip over your 45s. 30 more is 150. 30 more is 180. 30 more is 210. 30 more is 240. 30 more is 270. 30 more is 300. And 30 more is 330. 30 more is 360. And then we used our triangles. Let me see how I can zoom out just a little bit there. We used our triangles to label the ordered pairs. There we go. All these ordered pairs are based on the sides of a right triangle, and we had a triangle that had a 45-degree in it, a triangle that had a 30-degree angle, and a triangle that had a 60-degree angle for all those ordered pairs. Now, not only do you need to be able to count by 30s quickly, you need to be able to count by 45s quickly. So 45, 90, what would that be? 90 plus 45?
135.
135 plus 45 is 180, plus 45 is what?
225.
225 plus 45 is 270, plus 45 is
315.
315, plus 45 is 360. So you're going to be able to do that very quickly. Now, the one other thing I wanted to mention before we talk about any questions you have from 5.2, I want to make sure that you understand radians and can give the radian measure for each one of those degree measures that we have labeled. I used in the 5.1 video where the definition of radian is given, I used a rubber band that was the same length as the radius of my circle, and then I laid that rubber band around the circle, marking the different places that the rubber band would end if I laid it off around the circle. And we said if you have an arc that has the same length as the rubber band, an arc that has the same length as the radius, then this that I'm highlighting in yellow, and don't write anything on your circle yet, but this that I'm highlighting in yellow is a angle, some angle theta, and I'm going to write this in pencil so I can erase it. Some angle theta that is 1 radian. Theta being 1 radian just means that it is subtended by an arc that's exactly the same length as the radius. And if you keep laying that rubber band around the circumference of the circle, the second time it would end about right here. And the third time it would be almost to 180 degrees, but not quite. So if I use that for the terminal side of an angle in standard position, all the way from the positive x-axis to right there, that's a measure of 3 radians. Sorry. That's a measure of 3 radians. And then if I laid it off again, that's an angle with measure 4 radians. Laid it off again. That's an angle with a measure of 5 radians. And again, that would be an angle of measure 6 radians. And so we said this is a 360 degrees is a little over 6 radians. And we used the rubber band, folded it in half, and said, there's not quite a half of a rubber band length left. So we folded it in half again and said, oh, there's about a quarter of a radian right there. So 360 degrees is about 6 1/4 radians. And I didn't write quarter, I wrote half. That was our best guess using our rubber band, but then I said a quarter is about 0.25. 0.25 is darn close to 0.28. If that were 6.28, it would be what? What is approximately 6.28?
Isn't it
2 pi.
2 pi. So that's why we say, nasty eraser. We say 360 degrees is 2 pi radians. And from there, we can say, well, that would mean 180 degrees is what? How many radians? If 360 is 2 pi, then halfway around the circle is what?
It's just pi.
Just pi radians. And if halfway around the circle is pi radians, then a quarter way around the circle would be what?
Pi over 2.
Yeah. it's halfway to right here. And so what would 270 degrees be? What are we counting by with our 90-degree angles? Multiples of how many pi radians? 1/2, 2/2.
3, maybe 3 pi over.
Halves. Yeah, 3/2. And then another half would be 4/2, but 4/2 is 2. So when you're counting by 90 degrees, you're counting by half pi's. 1/2 pi, 2/2 pi, 3/2 pi, 4/2 pi. What does that mean 45 degrees would be in radian measure? If 90 degrees is a half pi, then 45 degrees would be,
1/4 pi.
yeah. So go around your unit circle and label all your 45 degrees in multiples of 1/4 pi. And this is 1/4. This is 2/4. And sure enough, 2/4 reduces to a half. And so what would 135 be?
3/4.
3/4 pi. And then 4/4 reduces to just 1 pi. And then what would 225 degrees be?
5/4.
5/4 pi. 270 is 6/4. We already have it labeled as 3/2. 315 would be what?
7/4.
7/4 pi radians. So you're going to get really good at going 1/4, 2/4, sorry, 0. I didn't start with 0. 0, 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4. Got it? Everybody say yes.
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 Yeah.
Okay, I just need to know you're alive. All right, let's go label our multiples of 30 degrees. If 90 degrees is pi over 2, what would 30 degrees be? 1/3 of that would be what?
3.
1/3 of pi over 2? 1/3 times pi over 2 is pi over 6
Yeah.
radians. All right, now we're going to skip our 45s and say if 30 degrees is pi over 6, then 60 degrees would be two of these. What does that round to? Not round to. What is it? What's 2 of these? Reduce to is what I meant.
Pi over 3.
Yeah, this is 1/6. This is 2/6. 2/6 is better known as 1/3 pi, or pi over 3. So we're going to get good at counting by 6. 1/6, 2/6, 3/6. Sure enough, 3/6 reduces to a half, so I'm still on track. What would this be? Give it to me in unreduced form.
4/6.
That's 4/6. Now reduce it.
2/3.
2/3. I write down 2/3 pi, but in my head, I'm still thinking 4/6, so that when I get to 150, I can call it what? Three, 6, 4, 6, what?
5/6.
5/6. By the time I get to 180, 6/6 reduces to just 1 pi. What about 210?
7/6.
7/6 pi. Don't forget your pi. Give me 240 before you reduce it. It would be what?
8/6.
8/6, and when you reduce it, it would be
4/3.
4/3. I write down 4/3 pi, but I'm still thinking 8/6. So 270 would be 9/6. 9/6 reduces to 3/2. No, I'm sorry. I was pointing at the wrong place. Yeah, 9/6 reduces to 3/2. So 300 degrees would be how many sixths?
10.
This is 9/6, this is 10/6, which reduces to 5/3. And what would 330 degrees be?
11/6.
11/6. All right, so not only am I going to get good at counting by 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, and 45, 90, 135, 180, 225, 270, 315, 360. I'm also going to get good at counting 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4. And I'm going to get good at counting 1/6, 2/6, 3/6, 4/6, 5/6, 6/6, 7/6, 8/6, 9/6, 10/6, 11/6, 12/6. All right, y'all practice that a bit tonight. So when you take test 3, oh, this is going to make me so sad. I'm going to have to change test 3 because it was basic. A big chunk of it was just to see if you have your unit circle memorized, because when you get to calculus, you don't need to take all day to say the ordered pair at pi6 radians. You just need to know the x. Let me label my quadrantal angles right here for just a second. This is 1, 0. That 90 degrees is 0, 1. 180 degrees is -1, 0. 270 is 0, -1. And then we're back to 1, 0. So the way that I remember all of my 45s, what did you notice about the coordinates, the x and the y, at each one of these 45 degree multiples of 45 degrees? What were the x and the y? Disregarding the plus or minus, what was the x and y at every 45 degree angle that wasn't also a multiple of 90 degrees?
Square root of 2 over 2.
Yeah, the x and the y were both square root of 2 over 2. Now at 30 degrees and 60 degrees, one of the coordinates was a half, 0.5. The other coordinate was square root of 3 over 2, and that's almost 1. So I know that for these two ordered pairs, either the x or both of the ordered pairs are either 1/2 or square root of 3 over 2. Which one's closer to 1 at 30 degrees? Is it x that's closer to being 1, or is it y that's closer to being 1 at 30 degrees?
X.
Yeah, x was 1 right here. Here, x should be just a little bit less than 1. That means my x is square root of 3 over 2. My y is a half. And that's exactly, oh, here's me being dyslexic again. Ooh, that 1/2 was my vertical distance on that point, and square root of 3 over 2 was my horizontal distance at that point. And then at 60 degrees, it's the y being closer to 1. When the y is closer to 1, the y is square root of 3 over 2, and the x is a half. And if you just draw a straight line down from that 60 degrees, if I had done this to scale, it would look like x was about a half, and my y is up here darn close to 1. So back to test 3 for a second. If we were taking this in person and you didn't have the unit circle in front of you, I am going to try to convince you that you wouldn't have to write down and label that whole circle to do well on this test. If you just remember if you just label the quadrantal angles 0 degrees or 2 pi, pi over 2 is 90 degrees, 180 degrees is pi, and 270 degrees is 3/2 pi. And then you just labeled your first quadrant angles, pi over 6, pi over 4, pi over 3, and then you wrote these 3 ordered pairs so that you could look at them very quickly. You could extrapolate this information for the first quadrant into the other 3 quadrants. Again, at all the pi over 4s, you know, both the x and the y are going to be square root of 2 over 2. When you're close to the x-axis, the x is almost 1. And when you're close to the y-axis, the y is almost 1. And you could use that to figure out the coordinate here, because x is closer to 1. You could use that to figure out the ordered pair here, because the y is closer to 1. So this is just something you need to practice. You can print infinitely many unit circles off the internet and just practice labeling them, label the whole thing a couple times, and then practice. Actually, at my math lab, not my math lab, in Momentum, I have a link to a great website to practice. It just gives you random angles, and you can set it to either ask you for the degree measure, ask you for the radian measure, or ask you for the ordered pair. Practice on that website and just see how quickly you can start identifying the ordered pair at each of these commonly used angles. All right, that was a lot of talking without stopping for a breath. Does anybody have a question? Is anybody still awake?
Yep.
Thank you, Will. Otherwise, I was about to go home. Wait, I am home. One other thing I want to show you. My completed unit circle. So with your Ziploc baggie of materials that I emailed you, or that I mailed you, it should eventually look like this, with all the degree measures, all the radian measures, and all the ordered pairs. If you don't have that finished, then finish it tonight and practice on the website that I posted in Momentum. All right. Now, the 5.2 homework that you were supposed to do tonight, or before today, you were supposed to attempt this day 1 homework in 5.2. I have to make you this day 2 video today. This is not available yet, but this homework and the text, and I think I already have that assignment in my math lab, the day 1 assignment. So what do you need to ask me? Let's start with the notes up to this page, number 48. And Kelsey, I remember Kelsey or Ashley emailing me about these simplify the expressions.
I think it was me, Kelsey.
Okay, all right, because this is going to take a lot of practice, Kelsey. We're doing something, well, I started to say unlike anything we've done before, but if you can compare it to something that you have done before, you'll eventually get more comfortable with it. If you can train your brain to look at this and go, well, no matter how ugly it is, it's like a difference of 2 squares over the easy kind of trinomial. If I know how to factor these 2 guys, I know how to factor these 2 guys, and I know I can cancel common factors. So It takes a little bit of practice, but I'm getting better at simplifying trigonometric expressions in the same way that I simplified algebraic expressions. And just in case I forget to tell you later, this page in Momentum, and I think I mailed it to all of you, is excellent practice simplifying trig expressions. So you not only have those 2 or 3 problems in the homework, but you also have all of these, and I posted the answer in Momentum. So do you have any questions from the 5.2 notes before we get to the 5.2 homework? Any questions from the notes or the video? All right. Let's just go to questions from the homework then. And it was the homework listed at the bottom of this page up to number 49. What do you need to see? Ms. Kelsey, did you get to feeling any better about them once you practiced a little bit?
Not really.
Not really. It's going to take a while. This is the most different thing I've ever seen in my life. Well, tell me one that bugged you, Miss Kelsey.
I'm still on 39.
Okay. We will get there. Ah, you know what? Your 39 was just a little bit more difficult than my 40. So don't judge all these problems by 39. I'm going to say when I did number 40 on the video, no, number 42 on the video, it was easy for me to recognize, hey, that's just the difference of 2 squares. And hey, that's just the easy kind of trinomial. What the heck is this numerator? Sine cube plus cosine cube. What special kind of factoring is that?
The sum of cubes.
That's the sum of 2 cubes. Now, if your hypnosis is still stuck with you, then when you say sum of 2 cubes, your hands fly up in the air and you make what 2 symbols? Do you remember what we did whenever we saw sum of 2 cubes? That was little parentheses, big parentheses. Binomial times a trinomial. In chapter 1, that was the handout that I gave you. I typed sideways to talk you through how to factor the sum or difference of 2 cubes. Is that ringing a bell, Miss Kelsey?
Yes.
Vaguely. Okay. All right. So let's try to apply it to this stranger looking thing. It's still a binomial times a trinomial. And there's nothing I'm going to do in the denominator. Now, I may have to look back at that handout from chapter 1 that says factoring the sum or difference of 2 cubes. The handout gave me the words that I used to talk myself through this process. But what do we start with? What was the first term of the binomial?
The cubed root of the first term.
Perfect. That's sine theta. And then what?
Plus the cube root of the second term.
All right, same sign, and then the cube root of the second term. And all of a sudden, I see what's going to happen here. This guy is going to cancel that guy. I just need to figure out what that trinomial factor is. Cube root, same sign, cube root, then what?
Square the first term.
Square the first term. What sign comes next?
The opposite, so minus.
Yep, opposite of that is minus, and then what?
Multiply both terms.
Multiply both terms. That's sine theta cosine theta. Last sign is always what?
Positive.
And then what do you do to get the last term?
Square.
Square the last term of your binomial, cosine square. So I did get that common factor that canceled, and what I'm left with is sine square theta minus sine theta cosine theta plus cosine square theta. And I'm so happy with myself that I just want to circle that and say it's my answer, but then I look in the back of the book and that's not what they have. So what should have leapt out at me in this expression that I have left? What should bells and whistles, bells and whistles should go off to say, hey, that's just what?
Sine squared theta plus cosine squared theta is 1.
Perfect. How about that? Does it make sense now, Miss Kelsey?
Yes.
Does that automatically mean if I gave you another one, it would make sense? No. It takes practice. It's supposed to make sense when you're watching me do a problem and listening to myself talk through it, but it just takes practice and practice for things like, oh, if I have 2 trig square functions, there's a good chance I'm supposed to put a 1 in, or a -1 in place of that. And to say, oh, that's just the sum of 2 cubes. That's going to take lots and lots of practice, and you're not going to feel comfortable with it today or tomorrow. But sometime next week, you should be saying, this is not terrible. This is getting a little better. And then in calculus, we're just going to use it and use it till things like that just leap off the paper at you. All right, what else do you need to see up to 49? Not the only question anybody had?
No, can you do 49?
Yes, because that, let me back up and say something here. I mentioned it, I remember saying this yesterday. I'm not sure what problem I said it on, but something we were doing yesterday, I said, if I had to find the derivative, whatever that means in calculus, if I had to find the derivative of something, I'm guessing it's a whole lot easier to find the derivative of this than it is to find the derivative of that. That's why we need to get good at simplifying trig expressions. Another reason is sometimes we do a whole page of calculus and we get, for example, this answer, and we flip in the back of the book and go, that's not the answer in the back of the book. Well, when you see the answer in the back of the book, you should be able to say, hey, my answer is equivalent to theirs. And that's really what you're practicing on number 49 when it says write sine in terms of secant. Certainly they're not the same thing, but if in calculus I look in the back of the book, or my answer has sine in it, and the answer in the back of the book has secant in it, I need to be able to figure out if my answer is equivalent to theirs. So I need somehow to be able to change sine to something with secant in it. So remind me real quickly, what are my 3 Pythagorean identities? What's the first one? The granddaddy of all. We used it right here. Sine square theta plus cosine square theta equals 1. What's the second one? Look at my notes. Somebody tell me so I know you're alive. Somebody other than Will and Kelsey, because they're the only 2 voices I've heard lately. Miss Ashley, are you there?
Yeah. The okay, so 1 plus tangent squared theta equals secant squared theta.
Good. I like making you say this out loud too, because it sticks in your head better if you read it out loud. What's the third Pythagorean identity? Who's with me? Who else is here? Ethan, did you come today? I don't think I saw Ethan. Oh, Carly. Carly, what's your third Pythagorean identity?
1 plus cotangent squared theta equals CSC squared theta.
Good. And what does CSC stands for?
Cosecant.
Good. 1 plus cotangent squared is cosecant squared. All right. So this process of writing sine in terms of secant is somehow going to have to use one of these Pythagorean identities. Sine is not the reciprocal of secant. Sine's the reciprocal of what?
Cosine.
No.
Is it cosecant?
Cosecant. Right. And that may have been what you were thinking and just said it wrong. But the definition of cosecant is sine is 1 over cosecant, or cosecant's 1 over sine. So start with what they said to start with, rewrite it in terms of its definition, but we still haven't done what we were asked to do. We don't have this in terms of secant yet. We only have it in terms of cosecant. So you look up here at one of your Pythagorean identities and say, does any one of those three tell me how to change cosecant to secant? Does any of them have secant and cosecant in it? No. All right, so maybe 49 is a little bit harder than 45 and 47 because none of those have both sine and cosecant in it. Let's think for a second. All right, I have an idea, but I'm wanting to not tell you. I'm wanting to help you figure it out. What if, instead of writing sine as 1 over cosecant to begin with, what if we had written sine in terms of cosine? I think if I can change sine to something with cosines in it, then I can change cosine to something with secant in it. And this is going to happen a lot in the next few days. We're going to try something. We're going to get stuck. We're not going to freak out. We're just going to say, oh, I need to try something else because I kind of hit a brick wall right there. So how could I use that first Pythagorean identity and get the sine by itself? What could I put in place of sine?
The square root of 1 minus cosine squared theta.
I'm glad you didn't leave off your square root. You'd have to subtract cosine squared from both sides, and then you'd have to take the square root of both sides. So that's true. Now, how can I write that in terms of secant? What could I put in place of cosine squared that would have secant in it instead?
Might it be 1 over secant?
Absolutely. Actually, 1 over secant squared.
Yeah.
Now, I've done what the directions said. I started with sine. I ended up with something with secant squared in it, or something with secants in it. So I have followed the instructions, but I doubt that the book is ever going to leave a fraction under a radical as the answer. So what could I do to clean that up a bit? Any ideas?
Could you square it?
Oh, I'm glad you said that, so I could tell you why that's not right. If I have square root of 7 and I square it, Do I have an equivalent expression? Is square root of 7 the same thing as square root of 7 squared?
Definitely not.
Definitely not. So if you have square root of 7 equals x, if you have an equation, it is legal to square both sides of an equation, but it's if you square just an expression, you've changed the value of the expression. Does that make
Okay.
sense, Will?
Yeah.
Okay, so watch out for that. That's a common logic error. Since I don't have an equation here, I just have an expression I'm trying to simplify, I can't get rid of the radical. That was a good idea, but it just would be illegal. So what else? I'm thinking it might be simpler if I got just a single fraction here. How could I get a single fraction? Somebody say get a common denominator.
Get a common denominator.
Yes, you could get a common denominator. You could write that 1 as secant squared over secant squared. And then when you added the numerators, you'd have secant squared minus 1 over the common denominator. Oops, I left my theta out of the numerator. Secant squared theta minus 1 over secant squared. Is anybody thinking, I don't see how that's equivalent to the line above it? I could put in a middle step if you need me to. All right, if nobody's asking for a middle step, let me say, I think there's one more thing I could do to simplify that expression. You see what it is?
You wouldn't cancel the secants, would you?
If you just cancel the secants, that would be illegal because you're
Yeah.
canceling terms. If you thought, well, I can divide both terms by secant, I could break it into 2 fractions, I'd say that would be legal, but that would be going right back to the step above. Would be
Yeah.
what computer scientists call infinite loop. So that would be legal, but not helpful. How do you simplify if I give you square root of 5/9? What could you simplify that to?
The square root of 5 over 3.
Right.
Oh, are we just separating the? So it'd be square root of secant squared theta minus 1 over secant square root of secant squared.
And what is the square root of secant squared?
Secant.
Yep. How about that? Now, something else just popped in my head because I'm all about Pythagorean theorems, Pythagorean identities today. When I see trig squared and a 1, my eyes automatically go, oh, I can probably simplify that. What does secant square minus 1 equal in terms of one of these identities? Which one?
The tangent.
Yeah, secant square minus 1 would be tangent squared, but look at the directions. Do these directions allow me to have a tangent in my final answer?
No.
No, I wanted sine in terms of secant, and that's why I'm going to stop right here instead of saying that numerator's just tangent. All right, this is going to take lots of practice, and it's going to be a while before you feel comfortable with it. What we're doing tonight, the video you're going to watch tonight on verifying trigonometric identities. By the way, I have an extra practice worksheet of that in Momentum as well. In Momentum, I have extra practice simplifying trigonometric expressions, and then a worksheet, extra practice verifying trigonometric identities. You need to do both of those because watching the video, you'll go, that makes sense, that makes sense, that makes sense, watching me do it. But what you don't realize until you try it is the hard part is thinking, what can I do next? If you don't having somebody telling you what to do next, you have to figure out what to do next. It takes a lot of practice to get comfortable with that. All right. We have about 4 more minutes. Anybody have another question? Going once. Going twice. All right. Let me make sure that you understand exactly what to do for tomorrow. You have My Math Lab section 5.2 day 1 homework. So you'll have some problems just like these we were going over. And then you have YouTube section 5.2 day 2 video. And then section 5.2 homework that's listed on the back of the notes. Day 2 homework. Is page 348, odds 51 to 77, 85 to 91. All of those are odds.
What numbers were those?
Look at the camera. I wrote them down for you.
Oh, okay.
It's also at the bottom of 5.2 notes.
Yeah, all right.
I feel like I'm almost giving you an unreasonable amount of work, way more than you would have if you were in class. But that's because if we were in class, you would have this day of lecture, you would have this homework, and you wouldn't have this. But this, remember, this is just 6 problems that if you've done the 5.1 day 1 homework in the book, then these 6 problems shouldn't take you very long. And this is just to make my life easier. It's a whole lot easier for me to give you 6 problems that my math lab will grade for you than to have y'all all taking pictures of multiple pages and emailing that to me. That might just drive me right over the edge. All right, any questions? All right, I appreciate y'all. Have a good afternoon, and I'll see you tomorrow morning at 9.
Bye.
Bye-bye.
Bye.
All right, bye-bye.